Hi everybody. This is our lecture on section 3.1. So starting chapter 3, this section is on integration by what's known as the parts technique. Okay, so recall the product rule. And the product rule states the following, right? If you have two functions, ux and vx, and you want to take their derivative, then that is the derivative of u times v plus u times the derivative of v. Okay, but let's write it like this. Let's write it as v u prime of x plus u of x v prime of x. All right. So now let's take the antiderivative of both sides. So if I take the same equation that I have here, just the product rule, and I just apply the antiderivative operator to each side, like that. Excuse me. Well, the antiderivative of the derivative is just the original function back. And let's forget about the plus c for the moment. And this is the antiderivative of vx u prime of x dx plus antiderivative ux v prime of x dx. Okay, so u times v is the antiderivative of v times u prime plus the antiderivative of u times v prime, right? The antiderivative of the sum is just the sum of the antiderivatives. All right, so let's move this term over here and this term over here, right? So let's rewrite this as the antiderivative of u of x times v prime of x is equal to u times v minus antiderivative vx u prime of x dx. Okay, so just juggling the terms around a little bit, that's what we get. And now what we do for shorthand notation, for a more compact notation, denote, right, v prime of x dx is just equal to the derivative of v. And u prime of x dx as just the derivative of u. So now we have the more compact formula. Antiderivative u times dv, antiderivative u times dv, just forget about the x, throw away the x, so v prime x dx we just write as dv, and u we just write as u, is equal to u times v minus the antiderivative v du. And this is the integration by parts formula. Right here. Antiderivative u dv is u times v minus antiderivative v du. Same thing goes with integrals. The integral from a to b right, right, so that's with just antiderivatives. And then if you want to do integrals, you can write it like this. The integral from a to b of u dv is u times v evaluated from a to b minus the integral from a to b of v du. Okay, so we can do antiderivatives or integrals using this formula. So here is a nice example, and this allows us to do antiderivatives of lots of functions that we have not really been able to do yet. So, for example, let's do the antiderivative of x cosine x dx. Remember, we did this one, or we did something like this one, in the section on substitutions. Here you would just let u equals x squared, and then because the derivative of x squared is x, give or take a constant multiple, right, that would cancel out that x and transform the antiderivative for x into an antiderivative for u. Okay, but that doesn't work here because it's not cosine x squared, it's just cosine x. All right, so here what I'm going to do is I'm going to let u, okay, be x, and I'm going to let dv, the derivative of v, be equal to cosine x dx. Don't forget the dx there. So the derivative of u is just 1, right, or just dx, is 1 times dx. And the antiderivative of the derivative of v, well, the antiderivative of cosine is sine. Right, you're supposed to have a plus c there at some point, but, we can just leave it out for now. Okay, we'll put it in just at the end. So we let u equal x, and the derivative of v be cosine x. So the derivative of u is just 1 times dx. And v is the antiderivative of cosine, which is sine. Right, so this is equal to, right, u times v, so that's x sine x, minus antiderivative v du. So here's v and here's du. So it's just sine x dx. Well, this antiderivative we know. Right? The antiderivative of sine is minus cosine. So in the next step, we get that this is equal to x sine x minus cosine. So it's plus cosine x. And then at the very end, when you have no antiderivatives left, then you put your plus c. So x sine x plus cosine x. Let's check this. All right, the derivative with respect to x of x sine x plus cosine x, okay, is equal to, well, it's the derivative of x sine x, and you got to use a product rule. So it's the derivative of x, which is 1, times sine x, plus x times the derivative of sine, which is cosine x, plus the derivative of cosine, which is minus sine. And these cancel, and you get x cosine x, which is what we wanted, because that's the original function back that we're trying to find the antiderivative of. Okay? Let's take another example. Let's do the antiderivative of x squared, e to the minus x dx. And here I'm going to let u equal the polynomial x squared, and I'm going to let the derivative of v be e to the minus x dx. So the derivative, once you find u and dv, right, we're going to be applying this integration by parts formula. Where is it? Right here. So we want to pick u and dv. You want to pick u and dv, and then calculate what v and du are, and then plug that into this formula here, the integration by parts formula. That's pretty bad looking. So we let u be x squared and dv be e to the minus x. Now, how am I picking that? Well, I'll let you know in a little how you go about choosing that. So now the derivative of u is 2x dx, and v, the antiderivative of e to the minus x. Well, you can solve that by a substitution, right? Let q equal to minus x, but I mean, we should recognize at this point that the antiderivative is minus e to the minus x. The derivative of e to the minus x is minus e to the minus x. All it does is, using the chain rule, it takes the derivative of the inner function there, which is just minus 1. So that's v. So this is equal to u times v. So it's minus x squared e to the minus x minus v du. Now, careful with your signs here. Right? I have 2x times e to the minus x, minus e to the minus x. So I'm going to bring that minus 2 out front. So it's going to be plus 2 x e to the minus x dx. Right? See, it was minus v times du. Minus the antiderivative of v times du. But see, this v times du has got the minus 2 in front of it, so I'm just pulling that right outside to get a plus 2. Now, okay, this is almost like what we started with. Antiderivative x e to the minus x, antiderivative x squared e to the minus x. So I'm going to apply that integration by parts formula again. So a second time, letting u be the polynomial x, and dv be e to the minus x dx. So du is just dx, and v is the antiderivative of e to the minus x, which is minus e to the minus x. So this is equal to minus x squared e to the minus x plus 2 times, apply this here. All right, that was u times dv. This is u, and that's dv. So that's going to be equal to u times v, so minus x e to the minus x, minus the antiderivative v du. So v du is minus e to the minus x. Bringing that minus sign out front becomes plus the antiderivative, e to the minus x dx. Almost done. So I have minus x squared e to the minus x minus 2 x e to the minus x plus 2 antiderivative e to the minus x dx. Antiderivative e to the minus x is, again, minus e to the minus x. So I've got minus 2 e to the minus x plus c, after all those antiderivatives are gone. And there's my final answer. Okay, and we can take the derivative and check that that derivative of this function here, okay, is actually equal to the original function there. So that would make our antiderivative correct. Okay, so how am I picking u and dv? Well, there's some rules of thumb that are often useful. So how to pick u and dv. Okay, if you've got, so this method often works. often, but not always. Pick u first and dv second in the following list of function types. So we've got L for logs, I for inverse trig functions, P for polynomials, E for exponentials, and T for trig functions. So given a product of two functions, logs, inverse trigs, polynomials, exponentials, and trig functions, pick u and dv in that order. U to be higher up on the list and dv to be lower down on the list. Okay, this will often work. So for example, how about antiderivative of x natural log x? Right, so I have a log and a polynomial. Right, so what does it say to do? Take the log first and polynomial second. So we're going to let u be that log function, and I'm going to let dv be equal to the polynomial. Right? Log, inverse trig, polynomial. So I got log and I got polynomial. And in the end, u and dv, the product has to be all of this. Right? The product has to be that whole thing. Right? So the product of u and dv is ln x times x dx, which is what this is right here. Okay, so now that I've picked u and dv, the derivative of u, well, that's 1 over x. And v, the antiderivative of dv, is 1/2 x squared. So this is equal to u times v, 1/2 x squared natural log of x, minus, so where's that integration by parts formula? Well, let's get it over here just for reference. Put it right there. Okay. So u times v, that was, here's the v, 1/2 x squared times natural log x, minus the antiderivative v du. So here's v times du. And the product is just 1/2 antiderivative of x. Right, because I have x squared times 1 over x. So what do we get here? It's 1/2 x squared natural log of x minus 1/4 x squared plus c at the very end after you've evaluated the last antiderivative. Okay? So there we go. There's one example of the usage of that list. And you'll notice in the previous examples that I did, we had these three types of functions: polynomials, exponentials, and trig functions. Polynomials, exponentials, and trig functions. All right, so over here, well, we had a polynomial times an exponential, so polynomial first, exponential second. And up above, in the first example, we had polynomial, that's first, and trig function, that's second. Okay? And notice in the second example, we actually had to apply the integration by parts formula twice. In the other two examples, only once. Here's another example of where you would apply the integration by parts formula twice. So let's calculate the antiderivative of e to the x cosine x dx. So here I have exponential function and a trig function. Exponential function and a trig function. So what I do is the exponential function comes first, and the trig function comes second. So the derivative of u is just e to the x, and v is the antiderivative of cosine, which is sine. So this, via the integration by parts formula, let's put it there for reference. All right, this is u times v, so e to the x sine x, minus antiderivative v du, e to the x sine x dx. All right, so now I'm going to apply the integration by parts technique again. Here again I have an exponential and a trig, so I'm going to let u be the exponential function and dv be the trig function. And the derivative of u is the derivative of e to the x, which is e to the x, and v is the antiderivative of sine. The antiderivative of dv is minus cosine. So, applying this again, we get e to the x sine x minus, now put a big parentheses there for our second application, minus cosine x e to the x, plus, also minus the antiderivative of v du, but I've got this minus here, so try to keep track of those minus signs. Let's see, I don't quite have enough space here, do I? Let's go down here. So it says e to the x sine x minus u times v minus cosine x plus antiderivative e to the x cosine x. Okay, something interesting happened here. So in my chain of equalities here, so I've got this is equal to this is equal to this. Notice that I've got that the antiderivative here is the same as the antiderivative here. Let's rewrite. Rewriting the equation, we get antiderivative.
I can learn to understand you much better if I can get familiar with the way you talk. I need your permission to help.
What did I do there?
I can learn.
There it is. All right. So rewriting this, we get antiderivative e to the x cosine x dx is equal to this, e to the x sine x plus e to the x cosine x minus antiderivative e to the x cosine x. So now what I'm going to do is I'm going to add this to each side because it's the same antiderivative. So I'll add it here. And I'll add it here. Or sorry, yeah, add it. I wrote subtract, but what I want to do is add it. So it'll cancel it out on the right and just give us two of them on the left. So I have 2 antiderivative e to the x cosine x is equal to e to the x sine x plus e to the x cosine x, and now divide by 2. So antiderivative e to the x cosine x is equal to 1/2 e to the x sine x plus e to the x, well, I'll just put it all over one fraction, over over 2. And once you get that final answer, you put your plus c in there at the end. Okay, so that's something that comes up once in a while. Okay, you'll have an anti-differentiation problem that you're gonna try to solve using integration by parts, and you'll do integration by parts twice, and then what you end up with is the original antiderivative is written in terms of itself. So that's the original, and then it pops up again over here. So that happens mainly with exponential times trig functions, whenever you have an exponential times a trig in some way. In which case, what you do is you rewrite the equation. You take your first expression, the original antiderivative, is equal to your last expression in the initial chain there. And you get this. And then you cancel additively on the right, adding it to the left, putting in some, extra coefficient, and then divide. Okay? So, final answer right there. Let's do one more problem, just the integration problem rather than an antiderivative problem. How about this? Let's see, well, what haven't we done yet? We did log time polynomial. Let's do this one. So this is an interesting one. So let's do the integral from 0 to 1 arctangent x, just by itself. Okay, with this one, okay, look at that list again. That list said logs first. Where did it go? There it is. Logs first. Inverse trig second. Polynomial third. Okay, so what's in that problem? All I have showing is an inverse trig function. But there's always a polynomial there, right? Just the number 1 by itself is a polynomial. So just dx by itself, that's a polynomial. So you can always take it to be that. So if you just have a single function by itself, sometimes you can do something like this and it'll work. So you want to let u equal arctangent x and dv be just 1, which is a polynomial, just polynomial that's constant, polynomial of degree 0. So the derivative of u is 1 over 1 plus x squared, and the antiderivative of dv is v, which is just x. Right? The derivative of x is 1. Right? So you see it's got some, it's got something to help us out here. So the integration by parts formula, I think I don't have it in my clipboard anymore. Where did it go? So here we're doing the integral from a to b of integration by parts, rather than antiderivative. So let's put this up here. Alright, so we've got that to refer to. So this is u times v is x arctangent x, evaluated from 0 to 1, minus integral from 0 to 1, v du. So that's x over 1 plus x squared dx. All right, so evaluating this from 1 to 0, right, that's arctangent of 1 minus 0 times arctangent 0, which is just 0, minus the integral. Well, this one, I don't know if you remember from the section on logs, this is almost of the form g prime over g. But I'll fix it up so that it is. Right, now this is of the form g prime over g. Right, so the antiderivative of that is the log of g. Right, so this is arctangent of 1. Well, arctangent of 1 is pi over 4 minus 1/2, and the antiderivative of this is natural log 1 plus x squared, evaluated from 0 to 1. So it's pi over 4 minus 1/2 natural log of 2 minus, well, let's see, like that, minus natural log of 1. Natural log of 1 is just 0. So it's pi over 4 minus 1/2 the natural log of 2. Okay? So that's a final example there, and that's the lecture for the section.